So we have to. So we are going to start again with the second session of the day. So now we have Leonardo de la Cruz, who is going to talk us about the classical Young-Mill amplitudes. Please, Leonardo, go ahead. Thank you.
Okay, thanks. So first of all, I'd like to thank the organizers for the invitation. It's a pleasure to be at least virtually in Mexico and in Puebla. I've never been. I'd like to visit from some point. So today I'm gonna talk about some work that I've done in collaboration with these people, my collaborators in Edinburgh at the time, Ben Maybe, Donald O'Connell, and Alasdair Ross, and also collaboration that I've done with Andres Luna and Trevor Sharpner. Trevor is a PhD student at UCLA, and Andres is now in Copenhagen, and some also work that I've done myself. So, the topic is classical Young-Mills amplitudes. So this conference so far has focused on some aspects. There was a nice review talk by Matt, but why we are in general interested in the structures that appear in amplitudes. So, I'll continue this now with this topic now of Young-Mills. So specifically one part of the area of amplitudes that is focused in Young-Mills, and more specifically in classical Young-Mills. So let me start by motivating this talk. So why we are interested into studying scattering amplitudes and observables. So the motivation, it's basically these two plots. So on the left-hand side, I have a typical plot of some experimental observations of cross-sections compared against their theoretical predictions. And so we know that in order to do these theoretical predictions and cross-sections, for instance, the modern approach is to use unitarity, spin helicity, color kinematics, duality, double copy, and so on, all the techniques that were mentioned in Matt's talk. And as he also mentioned, at the end of the day, one needs to solve some Feynman integrals, which are usually solved to differential equations if one needs to get these analytic results, for example, of cross sections. So now, on the right-hand side, I have another typical plot, this time the observation of a gravitational wave, which in principle is unrelated to the one that is on the left. So in this case, this plot exemplifies a two-body classical problem. So this means that in order to make this prediction theoretically, one has to solve a classical problem, which in principle can be done by solving Einstein equations. In general, we cannot do that. So one has to rely into different techniques, such as numerical general relativity, some effective field theory approach, and more recently, amplitudes. So what we see then is that amplitudes, at least for what I've learned in some recent decades, amplitudes are the core of now even these two different observables. Good. So that's what we have in mind when we study amplitudes, and in particular for Young-Mills, because we know how to do computations in this left-hand side, which typically, for example, QCD. So we know how to do predictions in QCD. And we know that there is this double copy that tells us that the basis of gravity, at least at the perturbative level, is Young-Mills. So through this double copy, then we can make some predictions also for gravity, and in particular classical gravity, by using this idea of double copy. So we'd like to study Young-Milstein. But before that, let me give an invitation example of the type of situation that we are interested in. So suppose that I'm interested in describing the scattering of two particles that interact via electrodynamics. So I have one particle which carries some electric charge, which I call Q1, and some mass, which is M1, and there's another particle that carries another charge and a different mass. Now I'm interested in describing this phenomena of scattering. So also I am assuming that there is some separation between these particles, which classically is different from zero. Good. So now I'm gonna make an assumption. So I'm gonna assume that I can do a power series expansion of these trajectories in powers of the coupling, which in this case, it's just electric charge. And I assume that at leading order, the particle just follows a straight line trajectory, like both particles follow straight line trajectories. Okay. Whereas at the first correction is just a deviation of this trajectory, which is a straight line. Let me just quickly mention that if you're welcome to interrupt any point of this talk to ask questions. And I do the same with the velocity. So I just take the derivative of this with respect to some proper time, and I also consider the perturbation of the velocities. So to describe this the scattering, then what I have to do is solve Maxwell equations coupled with the Lorentz force. And because I'm interested in solving this perturbatively, then what I do is to substitute my expressions for the position and velocity into the equations of motion of the particle, which is Lorentz force, and the equation of the field, and I solve them this coupled system. So what I do and what one does is then just at each order in perturbation theory, one solves each of these equations, and then the solution then enters into the expression of the field, and then we can continue this process. So, for instance, one particular quantity that I would like to know, so it's how the momentum of one of the particles, let's say particle 1, changes during the collision. So this is what I'm going to call as the classical impulse, which is the total integral over some of the proper time of the particle and the change of velocity over all time. So this is what I'm going to call as classical impulse. And since I can obtain my expressions for the velocity at each order in perturbation theory, then I can also calculate the classical impulse at each order in perturbation theory. So this is a well-defined problem in classical physics. So I have the scattering of two charged particles, and I want to describe the total change of momentum during the collision. So that would be the classical view of this problem. So now, how do I do it if I want to study, if I want to use amplitudes? So the amplitudes approach then, carries the name of Kossover, Maybe, and O'Connell, and it tells you that to obtain the same quantity meaning the total change in momentum of the particle 1 during the scattering, what I have to do is to consider this difference. The difference between the operator, the momentum operator of the particle 1, evaluated at the initial state, and the evolution of this momenta, or rather more precisely, the evolution of these states with respect to the out states. So in this case, this momenta is evaluated with respect to the out state, which then I can use the S matrix to evolve it to the initial state. So then these states psi here are both initial. And I take the difference. Because my observable depends on the S matrix, then eventually I can use my expression of the S matrix in terms of the transition matrix to obtain the observable in terms of amplitudes. So that's the idea of Kosover, maybe, and O'Connell. If I want to compute the classical observable, then if I want to use amplitudes, then I have to obtain this to compute this difference. To do that, and then take the classical limit, of course. So, and because I need to take the classical limit, then I have to I will have to restore some powers of h bar in my quantities. So that's part. Of course, I can opt of not doing that and do some other framework. So this is the framework of Kosover, maybe O'Connell, to get the classical limit. So, and then to properly do that, then what I want to do is to restore h bars in couplings. And because I'm going to restore h bar, I'm going to be using units in which h bar is different from 1, but still keep the system relativistic. So C equals to 1. One thing that I have to keep in mind is that when I restore h bars in couplings and my quantities, the dimensionless couplings are going to scale a bit different with h bar. So the dimensionless coupling for the electric charge now it's has this factor of 1 over h bar. The same with gravity, and in the case of Young-Mills, when we include color, then the dimensionless coupling now it's proportional to h bar. So this is going to be important for the case of Young-Mills, as I will discuss later. Another thing that I have to do when I use the Kosover, maybe O'Connell formalism, is that I have to make a distinction between the momenta of a particle and the wave number of a particle. This means that the particles that are massive are going to be defined, are going to be described by momenta, whereas particles that are massless, for example, are going to be defined by wave numbers, are going to be described by wave numbers. Because I'm interested also in taking the classical limit, then I have to define my in states as states that have sharply peaked momenta and sharply peaked position. Then I have to construct my states such that they carry this this wave packet. So this is going to make the job of giving me the notion, the classical notion of a particle that has a well-defined momenta and well-defined position. And also have to keep in mind that the scales of my problem have to satisfy these inequalities, meaning that the quantum wavelength of the particle should be much more smaller than the spread of the wave packet that I'm using to compute the classical limit. And this also has to be much more smaller than the separation of the particle. This is quite intuitive because this is what we expect for a classical situation. Okay. Good. So that's what I would do then to obtain to use the. So these are the rules that I have to use to obtain my observables in terms of amplitudes. So let's see an example. So for the case of the impulse, then if I introduce the expression of the S matrix in terms of the transition matrix, what I obtain after using unitarity is that the expression of the impulse contains two contributions. One contribution that is proportional to the amplitude, whereas another one that it's proportional to the square of an amplitude. If you think about the cross section, which is the observable that we are used to in high energy physics, the cross section depends on the square of the amplitude. So here there is something that is quite peculiar about this observable, the classical observable, and it's the fact that it depends linearly on the amplitude. So at leading order, this other contribution does not appear. So at leading order, what I have to do is just to compute the amplitudes, just tree-level amplitude. And after I insert my expressions of the wave packets, and I take this, and I take the classical limit. Okay, I have these expressions here. I haven't still taken the classical limit of the amplitude, and the expression of my observable has some overall h bar squared. So the quantity in brackets that I'm gonna define in a bit is what is telling me that I'm taking some classical limit. Then the next step is to restore h bars in the amplitudes and then perform a Laurent expansion in powers of h bar. Okay. If I do that, in this case, this is quite simple. So the amplitude has a contribution of only of a single Feynman diagram, where, as I said, the momenta of the mass, the momentum of the massless particle here scales with h bar, and that's why there's a h bar in the denominator. And notice that I'm using this notation in which I put bars to quantities that are wave numbers. So if I do this the Laurent expansion, you can see that only the first term in the numerator contributes, and crucially, there is some cancellation between this overall factor h bar and the factor in the denominator of h bar. So the moral is that whatever is inside my double bracket must be independent of h bar. So, and if if the quantity inside the bracket is independent of h bar, then the integrals associated to the wave packets then trivialize. So what I can do is simply set in the classical limit, set the momenta to its relativistic expression. So just simply make this substitution once the quantity in brackets does not depend on h bar. And what happens is that then my expression in the classical limit becomes this one, which I can integrate, and I obtain then my first correction to the impulse. So this is the change in momentum of the particle 1 during the collision. Of course, I can do the same if I follow this iterative approach. But this, in the case, of course, for the case of electrodynamics, this example is quite simple. But if you go off to gravity, this is going to be a bit much more involved. So one prefers also to use amplitudes, because in some cases also the expressions that you get could be much simpler. For example, if you use unitarity here inside the expression of the observable. Good. So then let's move to Young-Mills. So in Young-Mills, I'm also going to be interested into developing an KMOC formalism. So for the observables that I'm going to be interested, the operators are the charge of the particle 1, the momentum operator, the color charge operator, and the charge in the adjoint representation. Okay. So what I mean here by Young-Mills, it's the case in which I have two scalar particles charged under SUN, okay, and the usual Young-Mills Lagrangian. so they carry, the particles that are scalar carry different masses, and these are the definitions, so the usual definitions that I have in QFT. So so this is a scalar Young-Mills, if you wish. So for this model, then it seems that, well, I'm done, right? So I can do the same. I can compute the amplitudes. I can use the same algorithm that I use for QED, that momentum transfer, for example, the momentum transfer scales as a wave number. So there is a H bar coming that I have to restore H bars and couplings, that also the loop momentum scales as a wave number. And I can perform a Laurent expansion in powers of H bar. However, I still have to define what do I mean in the case for what do I mean by the classical limit of a Coulomb charge, for instance, this operator. So that's the task that I need to do now. To define what do I mean by this Coulomb charge in the classical limit, so similarly as I did with the case of electrodynamics, then I have to have some set of classical equations of motion for the particles, and there's another set of equations now for this Coulomb charge. So then the charges that are classical are this described by what is known as Wong equations. So these are the equations that are generalizations. So this is the equation of a generalization of the Lorentz force, and now there is the Coulomb charge is also is now also dynamic, so it has its own equation of motion. So whatever I do in the amplitudes side, I have to be consistent with Wong equations. So in particular, with solutions of Wong equations. Good. So that's what I have to obtain at the end of the day. So, but from the now let's go to the QFT side. From the QFT side, I can starting from this action, I can define a Noether charge of operator, which carries dimension of angular momentum, and this Coulomb charge, as you can see now, because of the dimensions, scales with H bar. This Noether charge operator satisfies the Lie algebra of the generators of the representation. Here, notice that I haven't specified the representation. Okay. So at the moment, I'm keeping this representation arbitrary. So it is natural to define the classical limit of the Coulomb charge as the expectation value of this operator taken with respect to some Coulomb wave functions. So these Coulomb wave functions have to do the job, similar job, that the wave functions that I defined before for position and momenta have to do a similar job, giving us the notion of a localized Coulomb charge. What does it mean? So that's what I do next. So then to define these states, first I know that single particle states will be tensor products of color and kinematics. So the states that control the kinematics will carry some wave functions, the wave functions that I defined before, these ones. Whereas there should be also some wave functions that accompany this state. It turns out that the states that I have to construct to get this classical limit color should be coherent states. To construct the coherent states, I can use something that's called the Schwinger bosons. Schwinger bosons will allow me to construct states that are irreducible in terms of some creation and annihilation operators. So depending on the group, I'm going to have different sets of creation and relation operators, and they carry this complex, in general, complex numbers. So these states that I have defined here, then I'm gonna make I'm gonna produce that that the color charges satisfy two properties. One property is that the expectation value of the color charge operator must be finite, and the other property is that the product should be such that I'm going to have the factorization of these two charge operators in this way. But for that to happen, it must be that the size of the representation that I'm choosing should be large. Here, my irreducible representation is labeled by N1 and N2. So the property that this product is finite is gonna look like some this expectation value is gonna be proportional to h bar and some N1. So when you take the classical limit, this quantity must be large. In fact, once you construct irreducible states and you construct in terms of coherent states, these two properties are satisfied automatically, and this is the result of some old work by Yaffe. Good. So then, my multiparticle states look as follows. So, for in this case now, I'm considering the case of a scattering. So each particle carries its own wave function, and carries additional wave functions here that take care of this classical limit of color. And of course, they are constructed this way so that these two properties are satisfied. But importantly, when one takes the classical limit, also one has to take in mind that the color charges that I'm using are going to satisfy this Lie algebra modified by some factor of h. So now I can construct a new observable, which is the color impulse, by again taking the difference between the operator evaluated at some initial state and some out state. And the out state I evolve with the S matrix, such that my observable then is just the difference between two quantities that are evaluated with respect to in states. Again, using the unitarity and the expression of the S matrix in terms of the transition matrix, I obtain that the color impulse contains two terms. One term, again, that is going to be proportional only to the amplitude, and another term that is proportional to the square of the amplitude. Now, because the momentum is a color singlet, the momentum impulse is not going to be very interesting, because then the momentum impulse is going to differ only from QED only by exploitation of color, some color operators. But because of these two properties, these color operators are going to factorize, so the result is going to be quite simple. So this is more interesting. It's also important to remark that although here I have defined my states to have this form, in general I can also define my observables not with respect to these states, with an arbitrary state. So these observables are going to be well defined in the quantum and classical region. So it just so happens that I'm using appropriate states to take the classical limit, which is the limit that I'm interested in taking. Another observable is now this color charge radiating from the scattering event. Notice that this one, because there is no radiation in the initial state, this is going to be a quantity that's going to be this depend on the square, only on the square of the amplitude. Also notice that the operator now it's this adjoint representation, and that the other observable, in addition, the other operator is constructed in a way in which it satisfies color conservation. I mean, this is satisfied at the level of the operator, so this is going to satisfy at the level of the observables. So similarly, as I did in the electrodynamics case, so if I have a quantities between these double brackets, then I have to perform these integrals, which trivialize once the quantity inside these double brackets does not depend on h bar. So that's what I understand by these double brackets. Okay. So let's see an example. So, and I move because the leading order is quite simple. Let's go to next to leading order. So if I want to compute the amplitude now, I have to have these Feynman diagrams. No, so the ones in red do not contain the three blue vertex, as you can see. And at one loop, the second term does contribute. You can think of this as the cut of some box diagram. So what is interesting is that because of the h bar factors that appear in the three gluon vertex, so after counting powers of h bar, it turns out that the quantity that depends that contributes in the classical limit, it's just given by these four diagrams, which are the same diagrams that you have to compute if you are thinking in QED, the pure QED case. So the classical contribution contains some color factor. What I have done to write this expression is to do a color decomposition, meaning that I take some of these, let's say I take a basis of color factors and then write my amplitude in terms of this basis of color factors. So in doing so, then I obtained an expression in which everything depends on this color factor or color structure, multiplied by this kinematic part that depends only on these four diagrams, which are the same diagrams that I obtained in that I need to do the computation of the classical limit in QED. Now, something interesting happens, is that I know already when in QED that the box and these crossed box diagrams, when I do the expansion in powers of h bar, are going to produce some terms that was 1 over h bar or 1 over h bar squared. These are singular terms in h bar, which, because the observables that I have constructed are well behaved, they should cancel somehow. And it turns out that it cancels due to the presence of this diagram here, the second contribution. But in the case of Young-Mills, there is a new player, which is the color, and the colors satisfy the Lie algebra that I mentioned before. There's some h bar appearing there. So there are gonna be some terms that are singular in h bar, right? That will mix with terms that are of order h bar squared due to the appearance of color factors. So there's gonna be some mixing. You can see this type of mixing as follows. So if you need to compute the color impulse, then you end up with the calculation when you need to calculate a commutator of this form, which I can write it in this way. Then after using this Lie algebra, you can see that there is a term here that is proportional to h bar squared. So this term, it's gonna cancel things that were singular in the amplitude. So things that were singular in QED are going to become contributions, classical contributions in the case of Young-Mills. So this is quite interesting. So then you have to be careful in doing these manipulations when you do the classical limit for Young-Mills due to this non-trivial interplay between color and kinematics. But if you are careful enough, then you can obtain an expression for the observable that looks like this. I forgot here. Well, this is a calculation that that we did recently with Andres and Trevor Schopner. From this formula, one thing that is interesting is that the appearance of these factors of structure constants, they appear due to color and not kinematics, meaning that these diagrams that contain a triglyon vertex are not the ones that produce these terms that contain the product of two structure constants. And the case of the momentary impulse is just identical to QED, except that there's some color replacement. As I said, the only modification in the case of Young-Mills and QED is just that the color factors, you have to take expectation of the color factors. Okay. So that's the result. So we can say that QCD is kind of similar to QED in the classical limit, at least with respect to the momentum and color impulse. However, this is not the end of the story. This is true if radiation is not included. So if we now move to the case of radiation, so radiation is simpler now because as in the sense that it's more familiar to the things that we know, that there is the observable depends on the square of something that depends on the amplitude. There is something squared. So at leading order, then you get this expression for the radiation kernel, which is the thing here inside these double brackets. And at leading order in Young-Mills, you have that all these contributions will that all these diagrams will give contributions. So indeed, if you do the calculation, then again I'm doing the composition in some basis of color factors. What I obtain is that the amplitude will have two parts that contribute classically, one of which will be obtained due to the contribution of the triglyon vertex. So after you do you take the expectation value, you obtain an expression for the radiation kernel, which, as you can see at the end, contains this structure constant. So the conclusion is that unlike the impulse, the triglyon vertex contributes to the observable if you are considering radiation. Good. So any questions at this point? Well, if not, let me just move. So to another way of doing, of thinking about the problem. So
you have 5 minutes left.
I have 5 minutes. Okay, good. So I'm just gonna wrap up.
Okay? Yeah, sorry.
So the other approach is the effective field theory approach, which is an approach that there are many ways of thinking about this EFT. So here, what I mean by EFT is just the approach by Chang, Rothstein, and so on. So here, what is, and I could have started with this, of course, is that these things that are mentioned about the cancellation of H bar are not present. So this is the end of the story, but let's see how it works. So suppose now that I have to solve the same classical problem, but now in some Hamiltonian way. So, and suppose that I have access to a perturbative Hamiltonian that has this form. So there are some contributions of the Hamiltonian. So I'm interested, of course, in solving this perturbative. So what I know is that, like, if I have access to the Hamiltonian, I can write my equations of motion and then perform the integrations. Again, expanding in powers of the coupling, I can express my my trajectories, momenta, and colors as in some expansion. Okay, so then I can just simply by considering these expressions in terms of the Hamiltonian, I can construct my observables. So if I am so for the purpose of this part, I'm going to use the center of momentum frame. So I have defined these variables. And now I'm going to do a matching calculation. So in the full theory, I have scalar QD, the theory that I considered before. And at leading order, I'm going to have that the amplitude depends on a single diagram and a single color structure. And at one loop, there is some color factor and there is some amplitude that, as we saw, it has only contribution of 4 diagrams. This amplitude can be written in terms of what is called as master integrals, where these coefficients D and C are coefficients that depend on the kinematics. And I'm going to be interested in matching this full theory calculation with an effective field theory calculation. And for the effective field theory, what I do is to generalize the approach by Chang, Rostan, and so on, and write an effective theory in which the Feynman rules are much simpler. There's only 2 of them. So the diagrams that are relevant for this effective theory are just the at leading order, just a single diagram, and then next to leading order is this diagram. Then, because I'm interested in the Hamiltonian, and I construct an ansatz for this potential, for the potential operator, which contains both of my color factors. Using this ansatz, then I can compute in the case of the full theory, I know how to compute the amplitudes, whereas in the effective theory, I just compute my diagrams. And I match the expression of the amplitudes at each order in perturbation theory. The result is that when I do this matching computation, I obtain the coefficients D1 and D2, which appear in my ansatz. And once I do obtain these coefficients, then essentially I've solved the problem, because I can do the integrals, and I've essentially computed my observables again. So this is another approach. And finally, something that you can do in a piece of paper, following conjectures by Baer, Luna, Robin, Shen, and Seng, we can define something that is called the Eichhoff phase, which is just the Fourier transform to impact parameter of space of these quantities. By taking using this Fourier transforms, I obtain this Eichhoff phase of each order in perturbation theory. One obtains 2 expressions for the Eichhoff phase. And it turns out that the results are quite simple. It can be written in this nice way, where I have defined some expressions for these parameters. Okay, so this is the end of the 3 ways of describing these classic observables in Janus. So I'm just going to skip all this part and go to the conclusion. So what I've shown is that one can extend the KMOC formalism for Young Mills. This was already existing for QED and gravity. We have seen that impulses, color impulse and momentum impulse, they're like QED-like, but this is not the case when you include the radiation. And we have also constructed the EFT Hamiltonian, including color. And I haven't said anything about this. For the outlook, so in gravity, the KMOC has been already applied to loop, and so of course the motivation of pursuing this work is just to use the double copy to obtain gravity. So it would be interesting to do that and see explicitly how one can recover the results in gravity, and something that could be cryptic for you is the inclusion of spin. So meaning that I'm allowing the particle that participates in the scattering to carry spin. So that's all from me. Thanks, and hopefully I finish on time.
Yes, thank you, Leonardo, for this very interesting talk. Yes, clap. We have time for questions. Very interesting questions. There is somebody, if somebody wants to raise the hand or just to speak, this is allowed.
Okay. Hello, Leonardo. I have my name's David, by the way, from Honduras, and I have a question about what observables are there any requirements for the observables that can be computed through this K-map formalism, or there aren't like any conditions that the observable must satisfy in order to apply this formalism? Because, well, in fact, I didn't know that it could be applied to color too, so color charge too. So I didn't know that. So yeah, my question is in general, like, are there any conditions that these observables satisfy in order to apply this K-map formalism?
So you mean, yeah, so the observables, what I have to, the way to think about how to construct them is to think about what are the allowed operators. So these states, the states that are in states, so they are states of momenta, so carry some wave numbers, some quantum wave numbers of momentum. So I can define only, I can define my observer with respect to which operators can I act on the states. So if my state, so in the case of here, so if in my final state, for example, I allow also to be some radiated momentum, in that case, I can also think about some expectation value of a momentum operator radiated, which is similar to what I did in my in this part. Oops, where is this? Here. Similar to what I did here. So I have to think of to what operators I can act on my states and the characteristics of my initial state. So for example, for the case of scattering, so I define my initial state to be a state of two particles, and they are labeled by some momenta, let's say of the particle 1, particle 2. So I can only act, on this state only with operators that are obviously act non-trivially. So I am allowed to take this expectation value of the pole, for example, because the single particle state, let's say for just one particle, my state also carries these additional quantum numbers. So I would say that that's what restricts what observables you can define. So if, for example, if so the case that I mentioned at the end was quite cryptic. I consider spin, then I have some additional quantum number, so I can define another operator that acts on my state, and I can construct something like the total change of spin, right? Which would have some expression like this one. That would be my answer.
Okay, I see. Thank you. And well, I don't think there's time for more questions.
Okay. So I think that we have to move, otherwise we're going to end it very, very late for us. Three.
Yeah.
Thank you.
Okay.
Thank you very much,
Yeah.
Leonardo. So we clap once again. And now we will move with to